Here's part 2 of our lesson. We just talked about velocity versus time graphs where the velocity is changing at a constant rate, and we've used this graph to show that the total change in position, which is the displacement delta d of an object whose motion is changing at a constant rate, is equal to the sum of the area of this rectangle and the area of this triangle. And that really just is delta d equals 1/2 v1 minus v0 times t plus v0 times t. So let's move over to our last note on the right hand side, last note on this page. Go ahead and write that down. Now, this equation or relationship, delta d equals v times t, is the relationship that we developed from the middle graph on the previous page. It's the area of the rectangle. V is the height, t is the width of that rectangle. This second equation or relationship is the delta d, the change in position or the displacement of an object that is changing its velocity at a constant rate. And we found that if we add the area of the triangle, which is this part, with the area of the rectangle, which is this part, if we combine those two, we get the total displacement. Now, we call this equation the equation of motion with constant velocity, and we call this equation the equation of motion with constant acceleration. Fortunately, this equation has not been simplified. And so, if we do some simplification, some bookkeeping here, and we can make these equations a little more tidy. First of all, delta d is just the change in position. It's the final minus the initial, or sometimes it's written as d1 minus d0. Also, acceleration, remember it's delta v, the change in the velocity, divided by the time, delta t. I rewrote this substituting v1 minus v0 for delta v. And I substituted t for delta t, just to simplify things. Now, if we, first of all, take this equation here, and we replace delta d with d1 minus d0. Also, if we tidy up this right-hand side, we get all the v0s together and all the v1s together, you end up with d1 equals d0 plus 1/2 v1 plus v0 times t. What this boils down to is the final position d1 of an object traveling with constant acceleration is just equal to the initial position plus the average of the initial and final velocity. So we just add the initial, the final, and the initial velocity together, divide by 2, and multiply that by the time. If we take the definition of acceleration and we rearrange it and solve for final velocity v1, you get another equation that's useful. v1 equals v0 plus a times t. This is a linear equation, and it is the equation of a velocity versus time graph where the acceleration is the slope. So it's just the slope formula rearranged. Okay, the next equation is derived from this first equation. And what we've done is we've taken this second equation, the v1 equation, and substituted into this slot for v1 v0 plus at. And again, without getting too complicated, if you simplify this equation, you get rid of v1. Sometimes you don't know the final velocity, but you know the initial position, you know the initial velocity, you know the time, and you know the acceleration. So this would be useful. In fact, put an asterisk next to this equation. It is the most frequently used in high school kinematics. And then the final one is not used very often. What they've done is they've rearranged again and substituted in order to eliminate time. Notice we've got both velocities, the final v1 squared, the initial v0 squared. We've got acceleration, and we have both the final and the initial position, but we don't have the time. This equation is useful if you don't know the time, but you want to solve for one of these other variables. Okay, that is the these are the four equations that are going to be used in solving problems in kinematics where you have constant acceleration. Now, I do want you to copy one more thing down in your notebook, and I'm going to flip to that page, and I'm going to give you a chance to copy down the top of it. It's going to go on the very next right-hand side. So go ahead and copy this down, pause it, and then in a second I'll move it up to the top. This page is some general information, and also it is some information about shapes of graphs. I've identified the variables used in the equations. This d0 initial displacement, it's the initial displacement from the origin, so it is a position. d1 is the final displacement, which is also a position. V is the velocity. If it has a subscript, then it's a velocity at a particular time or moment in time. And then t is the time interval, but we just drop the delta. Okay. Remember, the slope of a displacement versus time graph is the velocity. This is really important in kinematics. Now, if we have a displacement versus time graph that's a curve, the curve will probably be one of these four shapes. Okay. Now we know that the slope of the curve at a particular point can be found by drawing a tangent line to the curve at that point. So we can say the slope of the tangent line of any point on a position versus time graph that is a curve is the instantaneous velocity. In other words, it is the velocity at and only at that point. Now, we're not going to be asked to do that. You don't need to find instantaneous velocities. But you might be interested in figuring out what is happening to the motion. Is the motion going in the positive direction and speeding up? Is the motion going in the negative direction and slowing down? Is the velocity positive and the acceleration negative? Is the velocity negative and the acceleration positive? From these four graphs, we can find that information. So, you can use these as a guide. Now, the last part, if the sign of the velocity and the acceleration are the same, the magnitude of velocity increases. If they are different, the magnitude of velocity decreases. For instance, if I'm going in the positive direction, my velocity is positive. If my acceleration is positive, I will be speeding up. If my acceleration is negative, I'm still going in the positive direction because my velocity is positive, but I'm going to be slowing down. And that graph is going to look like this. So here is positive velocity with negative acceleration. Here is positive velocity with positive acceleration. These match, so velocity increases. These do not match, so velocity decreases. You can do the same thing with negative velocity. Here is negative velocity and negative acceleration. So the magnitude of velocity increases. The slope becomes steeper. And here, the velocity is negative and the acceleration is positive. So the slopes of these tangent lines decrease. The magnitude of the velocity is decreasing. Notice the slopes are still negative. Both are negative, so that means the velocity is negative, but the slopes are decreasing. Okay. We'll talk about that in class.